Okay, so there we are. We're recording. Just as a quick recap, I believe we were discussing oscillatory systems last time. And so we had started our modeling journey, if you will, by looking at first order minor feedback loop systems, molecules, if you will. And we looked at a bunch of famous ones, right? But they had one stock in the feedback loop. And we said, we can examine them both if they're linear with their exact analytical solution and find out about them, or we can use test inputs and put them into equilibrium, shock them out, and see how they respond. And then we said, we can take these individual little molecules that we've studied in isolation and hook them together in different ways to make bigger models, right? But pretty much all of those, all of our study was on these simple first order systems, right? And then we said, well, what's the next level of complexity above a first order system? And that would be, of course, a second order system. So now we have two stocks. And if you have two stocks in a feedback loop, it's a major loop. And if the major loop is negative, right, the chances that the system will oscillate. So we began looking at oscillation, right? And I think we concluded by saying we're going to take a look at Jack Homer's model, right, of worker burnout, and then we'll go from there. So let's do that now. I'm going to share my screen. And let's see if I go over here. Hang on. Oh, you know what? This is one that's in process. I forgot. I have so many simulators now. I can't remember. This one is something I'm just working on. So let me not go there. Let me go here. There's not even any buttons or anything there at the moment. So I clipped this thing from Newsweek magazine back in 1993. That's when Newsweek magazine was still a magazine. That would be this paper thing that would come in the mail and you'd open it and read it for the younger people among us. Do they even have any magazines anymore? I'm trying to think of everything's, online now and whatever. But at any rate, I clipped this from it. And this is when Bill Clinton was just inaugurated as president. So he won the 92 presidential election and the 96, but this was 92. He beat George Bush Sr. in November of 92. So now it's, October of 93. So he was early on in his administration. So the article says here, the little blurb, worried that White House Deputy Counsel Vince Foster's suicide last July was caused, at least in part, by overwork. That was a big scandal at the beginning of the Clinton administration. President Clinton resolved to slow down. He took a 2-week vacation and ordered his staff to ease up as well. 7-day work weeks were cut to 6 and work days to 10 hours from 15. But it was too good to last. As preparations for Clinton's healthcare speech reached fever pitch, most officials, including Clinton, resumed their workaholic ways. Burnout, according to one official, is a real fear. Okay, so this is an example of what Jack Homer found out was happening to him. So Jack Homer is a well-known system dynamics guy. He was John Sterman's roommate at MIT when they were system dynamics students. So he and John are thick as thieves. Jack Homer's doctoral dissertation, we're going to look at some of his doctoral stuff in the healthcare space. He's really a healthcare guy, healthcare policy guy. We're going to look at that a little later. But for now, when he was doing his doctoral research, Jack noticed that he would work like a crazy person night and day on his dissertation, to the point at which his hands would kind of cramp up. And he was just totally burned out. Now, Jack is a California kid, so he would fly home, go to his parents' house, go to his bedroom he grew up in, and his mom would do his laundry and cook for him and whatever. He'd sleep in late. He'd gradually relax. The cramping in his hands would go away. he'd you know, kind of recharge his batteries and come back to school. And what did he do? He'd ramp it, you know, he's energized again. He'd ramp it up right away and was working like a crazy person until his hands would cramp up again. He'd be all burned out and so on and so forth. And he noticed, hey, there's a cycle going on here. And I'm a system dynamics person. So, you know, there's kind of a pattern here. I'm wondering if I can build a system dynamics model to investigate why this is happening. So he started looking into the literature, and guess what? There's a big literature in worker burnout. There's a literature in psychology. There's a literature in management science, and there's a literature in military science, because this is a quite a common phenomena. So people are gung-ho, they work very hard, they burn out, they back off, they recover, then they go and do it again, as though they didn't learn anything, right? So why is this happening? Now, Jack found out that in the literature, reading these literatures, there's all different explanations for why this is happening. And some were actually contradictory. So one of the nice things about system dynamics is it allows one to sort through the literature on some behavior, right? And see what makes logical sense, what doesn't, and test different hypotheses about what might be, you know, underlying some of these dynamics, right? All right, so having said that, Jack came up with this. Now, he published this in a paper in the System Dynamics Review, I think in 1985, early on in the life of the journal. Now, one of the things that is more of a let's end the course kind of topic is documenting a system dynamics model. So we've gone through presumably the process of how you build one, following good practice, and it does what it's supposed to do, and it's insightful, whatever. Now, how do you write it up so that others can follow what you've done? So it's kind of a mundane area, but it's quite important. Well, part of that process is figures. How do you make good figures that allow a reader, somebody who hasn't built the model, to understand what you've done? So this is Jack's attempt to explain the 5 most important feedback loops in his model. Now, I like this. I actually don't care for this particular way of doing it in and of itself, but I give Jack a lot of credit for trying to be innovative. Like, what can I do to convey to an audience the important feedback processes in my model? So I give him a lot of credit for trying something new and different here. So let's try and talk our way through why there's this cycle of burnout that seems to happen again and again and again in all walks of life. So we'll start over here with the perceived adequacy of accomplishment. Okay, so this is, you got stuff to do, a backlog of tasks to do, okay? And you have some idea of how much you should be doing, right? So that, if you compare what are you actually doing with what you think you should be doing, right? If there's a gap there, you feel somewhat inadequate. I should have gotten more done than I did this day or this week or whatever. Okay, so with loop number 1 here, what's your response as your perceived inadequacy goes up, or your adequacy goes down? I should say your hours worked are going to go up. I should have got more done and I didn't, so I'll just work more hours. Okay, and then that will make your accomplishments go up and your perception go up. So you have a negative loop there. You have an itch and you scratch it. I'm not getting enough done. I'll work more hours on it. I get more stuff done. Makes complete sense, right? So that's loop number 1 here. Okay. Loop number 2. And this is very key to his model. When your perceived adequacy of your accomplishments go up, so I'm getting a lot done. I think I should get 10 things done and I got all 10 done. What does this say? What does the plus sign there say? How do you reward yourself for being adequate, for getting your stuff done?
You expect more.
You ramp it up. You say, my goal was to run a 9-minute mile, and you work hard and you accomplish that. What's your reward? Well, I can do an 8-minute mile. So you work harder, you get down to 8-minute mile. What's your reaction? I can do a 7-minute mile, right? So, and then of course, when you ramp up the bar, your perceived adequacy goes down. Now you're inadequate, right? You got to work more. So people who are wired this way are susceptible to cycles of burnout. Okay. Folks who, for whom loop number 2 is not very strong, tend not to fall into this trap. Okay. What else do we got going on here? Well, let's see. Loop number 3 is going this way here. So again, Jack is trying, you see that there's these cross hatches, and it's a little hard to see, but there's different line thicknesses where he's trying to, in one figure, talk about it in the text of the paper and then refer the reader to the figure, but see the different loops. So loop number 3 is going this way here. It's a positive loop now. Okay. So when your perceived adequacy of your accomplishments goes down, you feel inadequate, your energy level goes down, feel depressed. Okay. And when your energy is down, your ceteris paribus, everything else remaining the same, your weekly accomplishments go down and you feel even more inadequate. Okay, so there's a psychological factor going on here. That's loop number 3. Loop number 4 is a positive loop, right? And that's going through this way here. So this is the thick line where he's trying, if you can see my cursor, it's going this way. So when the perceived adequacy of your accomplishments goes down, you work more hours, they go opposite direction, they go up. So your energy level goes down. Now your physical, the last loop was a mental thing. Now you're physically draining your energy. When your energy goes down, your accomplishments go down and you're perceived to be more inadequate. So you've got a psychological energy drain and a physical energy drain. And then the last loop, number 5, you can see is this cross-hatched loop. When your energy level goes down, your hours work per week are going to go down. You're just too tired, and that allows you to recover, and your energy level will go up because you back off. Okay, so those aren't the only loops in his model, but those are the main ones, and they help to tell the story of his model to someone particularly who didn't participate in the creation of the model. So you can use a causal loop diagram to brainstorm, but you can also use it to document a model and or present the basics of the model to an audience without getting into equations or, for that matter, every single loop, just the main ones that kind of tell the story of your model. And that's what Jack nicely did here. Okay, so this is just the what I discussed there. Again, I'm making this into a simulator. I haven't finished it, but that's basically what I just said. Okay, so what do we got here? Let me move this out of the way. Here's the base run. And in fact, let me see if I have it here. Oh, no, I didn't put it into the sim. So what's interesting is this. And again, this would be better in if I had completed the simulator, but everybody can see the 3 sectors here. Mm-hmm. Okay. So if we look at energy, okay, so basically there's energy recovery and energy drain, right? So you're going to, the more hours you work, the more you're going to drain your energy. And there's a normal drain per hours worked per week, okay? But then there are these effects, the psychological effect of your perceived adequacy and the hours worked. Okay, so they're going to drain you. If you're depressed and or really working a lot of hours, you're going to drain your energy above the normal rate, right? And then, of course, you got an energy recovery thing going on here. When you back off, you can recover quicker, right? Hours worked here is a function of what? So we have the indicated hours worked, and that this adjusts to that. That's molecule number 3, by the way, that you've seen before. Okay. And that's your perceived adequacy of your accomplishments. If you don't think you're doing enough, you ramp up the hours you've worked, right? And then if your energy is going down, you bring you back off, right? Saw that in the causal loop diagram. And then here is the structure for this, the psychological factor, the bias towards always trying to do better, ramping up your goals and what have you. So here's again molecule number 3, where your perceptions of your accomplishments. There's an expectation structure that's simpler than it's really the perception structure than relative to my Harrod structure, but there's not a growth thing in here. So Jack's a very good modeler. He knows about steady state error stuff. So he didn't feel he needed that in this case. Okay. So, and again, there's all the equations, so we don't have to at this point dwell on that. But what Jack found is that there were 5 places in the model that to which the model was sensitive, 5 leverage points. So, so if we just run the base run here, you can see you get the worker burnout base run. If you go to his paper, you'll see this exact graph. So here's the energy level falling and recovering. That's in red. And your hours worked, right, per week is, you know, you build it up. You're working like a crazy person. You peak over here, and then it drops off. And then you got a little bump here. It's kind of an interesting, it's like a heartbeat, a period 2, you know. And then there's a perceived adequacy of your accomplishments in, excuse me, in green. Now, this is, I presented these 3 variables in this graph because that's what's in his paper. Okay. I haven't really noodled through if that's the best way to do it, but it's in his paper, so I thought. So what are the places where his model is sensitive, where you got a leverage point, where you can change the behavior? Well, the energy recovery normal and the energy drain normal. So again, if we go back here, see, I flagged it. My style is to put it in different colors over here. So these 2 parameters here, the model's quite sensitive. So this is something of a physiological thing. You know, some people will run around the block and be exhausted and they'll be shot for the day, and other people will run, you know, 10 miles and be fresh as a daisy, barely sweating, right? So different people have different amount or lose their energy or burn their energy more quickly than others. And similarly, some people recover more quickly than others. So that kind of is a thing that's very personal to the person. So the energy recovery normal and drain normal, the model's sensitive to that. So that's a physiological leverage points. You know, you might be able to change these by way of training or something, you know, working out or something like that. Here's sort of a policy. So this is physical. Here's a policy lever. So this is hours worked, limit on hours worked. That's in that little blurb, Clinton talked about, or the article talked about how Clinton's resolved to slow down. He took a 2-week vacation and ordered his staff to ease up too, right? So you can say, everybody go home, right? So, so this would be a policy kind of thing. This would be a physiological thing, policy thing. And then this is that psychological thing where you're wired to always want to do better. And there's a table function impact and a parameter impact. And they're both involved in this psychological thing. Okay. So, so that's your base run there. So if we restore it and we say, well, what if we, instead of working 80 hours a week, we work 75 hours per week. Okay. What happens now? Well, that didn't fix it. It looks like it stretched things out a little bit, right? But okay, interesting. Is there any way to, what do we say, 75? What if we go to 72? Oh, okay. So that seems to stabilize things. So notice we got rid of a oscillatory system. We want a stable system. Okay. Now, what are we at? Hours worked per week was 72. That's still quite a lot, right? If we go to 70, more stable, there's a little less wobbliness there. I guess I could have made this even lower, but get the idea. Okay, so let's get the base run up here again. So that's the base. So you could address it with policy. Send people home, lock the doors. Now, some people, they work from home, they bring a laptop, they're going to work anyway, even if you lock the doors, right? How about changing their physiology? They train, they go running a lot, so they don't drain their energy as fast. So they have a more robust constitution. They eat better, let's say. So it's 0.06, 0.04. Let's try that. Oh, big impact, right? Okay. How about you recover more quickly? Let's boost that a little bit. I don't know, just 35. Oh, no. 35 didn't get us there. How about 40? Okay, so it's a little, you have to pound on that parameter a little more. Probably because there's I think there's the psychological component in the energy drain. So that's probably why that is. Okay. And then the bias fraction, how biased are you towards, or how much are you wired to aggressively always ramp up your expectations of yourself? So if we drop those a little bit, it looks like it's stretching it out, drop it a little more, stretching it out, drop it even more. Okay, so that seems to work. And if you look at his paper, you can also, and this is just about a Stella thing, you can change a table function. Okay, so we could just for the heck of illustrating this, we can change the table function a little bit here. And let's rerun it and see if that makes a difference. That particular change. Now that change goes along with the psychological wiring. So, you can try different shapes here, but of course they all have implications for, for the real world, right? So we're just kind of willy-nilly showing you that, but those weren't quite ineffective, right? So you could try and figure out in terms of the shape of the table function, then what that means, right? It's not just, again, it's like we want to make sure there's a real world. So in that case, what do we got here? Hours worked per week. That's no good. We stopped the oscillation, but nobody's working at all. So it's quite sensitive to this, right? So that's kind of interesting. So let's see how we're doing now. Still, okay. So, this is quite, so we could restore it to its normal, its normal position here. So out here in the tail, I can't remember exactly the psychology here as I do this, but you can get the idea. You can play around with this and say, in the real world, what would this mean for somebody's sort of wiring? Okay, so the idea there is we're going to, we have a system that's oscillating and we want to make it stop oscillating, or at least dampen the oscillations, right? And I like that model because it illustrates leverage points, right? Where a little bit of a change can cause a big significant impact, changing the way the airplane flies, right, so to speak. Now, some of that was parameter stuff. So quite often, system dynamics models are insensitive if they're feedback rich. If there's a lot of feedback loops, they're insensitive to to changes in parameter values. But sometimes they're not. It just depends on the situation. All right, cool. Cool. Now, let me show you something else here. I need to bear with me 1 second here. What is this? I need to find a browser here somewhere. So many things happening simultaneously here. Almost there, bear with me. Okay, so wait 1 second. Hang on. Where are we? Okay. Can you see my screen now? The Latka Volterra stuff? You can see that? Okay. How many people have ever heard of Latka Volterra? Raise your hand. Don't be afraid to step forward. So, hey, if you have, sorry, I'm grabbing, there's all sorts of things open here. All right. So
I know predator prey, but I don't know Latka Volterra.
Okay, so Latka Volterra is a very, very, very famous dynamic model. It's a predator prey model. Okay. And it was done in like 1926, I think independently by both Latka and Volterra, and they published them in the same year. I don't think they worked together. And it's a model that allegedly says, all right, this is how rabbits and coyotes interact, kind of an ecological system, sharks and little fishes, whatever, right? Okay. So having said that, so I want to emphasize, this is super famous. Okay, so I made it bigger. You can see it's bigger. So here's the model right here. So let's pause for just a second here and ask the question, tell me what you see with those two equations, if anything. This is like one of those ink blot tests, Rorschach tests. What do you see? Any thoughts on what you see right now?
They seem inverse of each other, reflexive of each other.
Okay, how about even more fundamental than that?
It's non-linear.
It's non-linear, so it's breaking the linear template. That's right. Okay, good. What else do you see? What are those two equations? Just at the most fundamental level, you see two flow equations, right? So anytime you see something like that, you should say, I see two flow equations. They are flowing somewhere. So where would they be flowing?
To the stock.
Okay, all right, to stocks, yes. To what stocks? dx dt is a flow flowing where?
To X and Y.
To a stock called X,
Mm-hmm.
right? And dy dt is a flow flowing to a stock, called Y. Okay. So right out of the box, as soon as you say that to most mathematically oriented people, they're like, what are you talking about? Then you mention, there's feedback loops in there. And then they're like, they don't know what to do, because they're typically, even mathematicians aren't typically taught to think this way. Okay. So right there, we have insights that most, not all, but most mathematically oriented people like engineers and stuff are unaware of. Okay, so we got two flow equations, and they're flowing to stocks known as X and Y in the traditional presentation of the Latka Volterra model. Okay, they're nonlinear, meaning we're breaking the linear template, meaning there's going to be some, in this case, stocks that are multiplied together. That breaks the pattern. If you multiply two stocks together, right, that breaks the pattern. But you have to, because if you want the predator and the prey to mathematically interact, well, then, of course, you know, you got to, the two stocks, the coyotes and the rabbits have to mathematically interact somehow, right? Okay. So it turns out, if you read here, the variable X is the population density of prey, or it could even be just the population of prey, and Y is the density or the number of predators, okay, like rabbits and foxes. Okay, so let's bear in mind what that is. Oh, this is a different thing. Let's close this. And let's plop down something that we're going to call X. I'm going to make this bigger so folks can see it. All right. And let's pop down another stock and let's call that Y. Okay. Now, just reminding us over here real quick, we need X and Y. We got those down. We need flows, dx, dt, and dy, dt, right? So let's get that a flow here. And let's call this dx dt. And yep, sorry, I got the jitters there. Oh, come on. Go this way. We're going to call this dy dt. Okay. Now let's look here again. I notice that I got a minus sign here and a minus sign here. Okay. And implicitly there's a plus sign here and a plus sign here, right? So that tells me we got outflows and inflows. So these are net flow equations because I got minus and plus signs going on here. So if I'm going to do net flows here, what do I got to do? Over here, I got to make it a biflow. And over here, I got to make it a biflow, right? Yes?
Mm-hmm.
Okay. So now what else do I need? I got X and Y. I got those down. I got dx dt, dy dt. Cool. Alpha, beta, delta, gamma are parameters. See, it literally says parameters here, right? So alpha and beta describe respectively the maximum prey per capita growth rate and the effect of the presence of predators on the prey growth rate. The predators parameters gamma and delta respectively describe the predator's per capita death rate and the effect of the presence of prey on the predator's growth rate. All parameters are positive and real. Okay, cool. So what we really need to do for our purposes is say, all right, I need alpha, beta. Notice if I just say beta, Stella will object because it's a reserved word. Same thing with gamma. And then delta. Okay. So alpha and beta go up here. Alpha and beta. And delta and gamma go down here. Okay, so so far so good, right? Nobody is panicking or not understanding. That's fairly straightforward, just representing what's up here, right? Now, in the flow equation, dx dt, we're told it's alpha times x minus beta times xy. So what we need to do is go over here. And we're told it's, it's going to be alpha times X. So I need X in here. And beta times X times Y. So I need Y in there. Right? So can you see on the side here? On the right side of the panel? Over here? Can you guys see on the right side? Okay. So we're told it's the net flow equation is alpha times X minus beta times X times Y, right? So let's confirm that that's true, right? Alpha times X minus beta times X times Y, yes?
Mm-hmm.
Okay. And then we're told that dy dt is delta times X times Y minus gamma times Y. So I need Y. I need X. Okay, so in here, it's delta times X times Y minus gamma times Y. Again, let's confirm that that's what we got here, right? Delta times X times Y minus gamma times Y. Okay.
Do we have to put parentheses around any of that in that equation?
Now, we can if you want. You want to do that?
I mean, that just for some reason I feel like
Well, there's an order. So the computers solve equations in a particular order, right?
Mhm.
So they'll solve anything in parentheses first, then they'll go to exponents, then they'll go to multiplication and division, then addition and subtraction, right? So as long as as long as your file you don't have anything that violates that, you're good to go. Okay.
Mhm.
So lack of voltaire. Okay, so we both agree, or we all agree that that is we faithfully represented that, right? Okay, so biological interpretations and whatever. So what do we have here? Here's some actual data. Okay, on predator prey. Okay.
I'm sorry.
And-
Just real quick. Could we run through the modeling, how the model models the equations again, if you don't mind?
No, I don't mind how the model models the equation. Sorry, not.
The one we just drew, how that translates to the equation directly in the different.
The first thing we notice is that these are two coupled first order nonlinear ordinary differential equations. That's the math talk. Basically, as soon as we see dx dt, dy dt, dz dt, d whatever dt, not a partial derivative that looks like a 2, a d that looks like a 2, but a regular d, regular small d, we know that we have an ordinary differential equation and we're good to go with system dynamics. Partial differential equations, no. Ordinary differential equations, yes. And they are kindly separated for us. You're going to see later that mathematicians like to scrunch things up. Instead of going, I want to sum from 0 to 1,000,000, they could write 0 plus 1 plus 2 plus 3 and keep going to 1,000,000. Their hand is going to fall off. So instead they write the summation I equals 0 to 1,000,000 of, I, right? They compact everything. So sometimes they'll take those two equations and compact them. Then you got to decompact them first before you can do what we're doing. But in this case, it's already decompacted. They show you the two first order systems that are coupled. Okay.
Mhm.
So you just have to know that the math that we're doing with Stella is that. So
Okay.
that just requires knowing that. Okay. The next thing I said is I noticed that in each of the equations, there's a minus sign, minus beta times xy and minus gamma times y, right? So that tells me there's stuff going in and stuff going out. But it's in one equation, so it has to be a net flow. The ins and the outs are in the same equation, rather than there's an inflow equation and a separate outflow equation.
Mhm.
If the ins and outs are in the same equation, it's a net flow equation, and we have to use a biflow. Okay. Then I just said, well, dx dt flows to a stock name X, dy dt flows to a stock name Y. So let's lay that out, dx dt, dy dt, and the stocks. And then the equations are fairly straightforward. It literally tells us dx dt is alpha times X minus beta times X times Y. And that's what we did right there, and so forth. Okay. Now, when you're building an original model of pressures from China and North Korea to cause mayhem in the Pacific or something, you're not looking at Lotka-Volterra equations. You're going to be doing it from scratch just with system dynamics. But at this point, we're learning about small models, major and minor loops, and how they interact, and oscillation and stuff like that. But you don't have to worry. You're not going to be, when you're really doing system dynamics for a research project, for some kind of study, you're not going to be dealing with this unless you're replicating somebody else's thing. Somebody in the Department of Defense wrote a paper and has equations like that. You can say, oh, I can take what you've done and show you how it would look like in my world. I'm going to translate it from Russian to English. Same thing, but it's in a different language, the language of system dynamics. Okay, so it's a nice skill to have, right?
Yeah.
Now, the good news is you're not going to usually see a model like this with 15 of these. You might see 1, 2, or 3 equations typically, and that's it. Because back in the day, when they were doing this on scratch paper, they couldn't handle more than that. So these famous models that tend to be very small.
So is there something in the way the model is put together that lets you know that alpha is being multiplied by X and beta is being multiplied by
Well,
X?
so these are the math people. There's normally an asterisk in there or an X, so it's multiplied, but when they don't show it, it's implied.
Yeah.
Why they like shorthand.
I just mean in the model itself, because alpha and beta are both going into dx dt. And then they're like, I guess once it hits that, it's like, if I was gonna reverse engineer this,
Mhm.
would it be possible to reverse engineer from the model to the equation?
From the system dynamics model?
Yeah, just from the representation that's here.
Oh, okay. So you were given this.
Right. Yeah. Would I be able to? Is that
So yeah, you would. So you wouldn't see this or this. You would just see this. Dx dt equals. See, it's a little small. You see dx dt equals right here. See,
Yeah.
equals alpha times X minus beta times X times Y.
okay?
And then this down here. I mean, we put in the parentheses, but and
Okay.
those are those two equations. Right?
Gotcha.
So in the traditional presentation of this stuff, you don't see the stocks. They're there, but you don't see them. You don't see the feedback loops. They're there, but you don't see them. That's what I was saying earlier, that it blows the mind of even mathematicians and engineers and stuff when you say, oh, there's stocks and there's feedback loops. They're like, what? You know, they're not used to thinking about even their own stuff in that way. I love doing that to economists. That freaks out the economist. Like, what do you mean? I don't know what the hell you're talking about. What do you mean? even if it's their original model, I've freaked out some economists. They're sort of big shots, and I'll say, oh, I like the feedback loops in your model. What do you mean? What are you talking about? Let me show you. They're like, I didn't know that stuff was in my model. Yeah, see? So, all right, before we go further, we got little warning triangles here, right? So that would tell us that the model is not yet ready to simulate, right? We've got to, if they're in the stocks, the most likely the problem is we got to specify initial values. And then these are parameters, they're just weights. We got to give values to those. But before we even do that, what do you see? Right here.
You see something that's it's a two stock
Second order system.
independent. there's an interdependence, so you're gonna have potentially oscillations.
Okay, so we have a second order system.
Mhm.
I see one major feedback loop and two minor feedback loops. And if you remember last time, we were looking at one major negative loop and then a major and a minor positive, major, minor, major negative, minor negative. It was damped, it was explode, and all that stuff. So this is in that same neck of the woods, right? We don't necessarily know what the details of this are, these loops, because we have to really nail down these parameters. And I'm wondering if they give us in this wiki thing, if they give us values here. Sometimes they do, sometimes they don't. What are they doing? What are they doing? You can linearize it. Yeah. Blah, blah, blah. So I want to see if we can get this.
Go back up. Go back up. That's where they had it.
Yeah. Okay. So if the
10
initial density
rabbits,
is 10
foxes.
okay. So 10 rabbits and 10 foxes.
Yeah.
Okay. So that,
Per square. Yeah.
yeah, it doesn't have to be density. You
Yeah.
can interpret it that way if you want. It's 10 and 10. And then from that, let's see. The growth rates and death rates of rabbits are 1.1 and growth and death rates of rabbits. So X's are the rabbits. So this would be, I guess, 1.1, they're telling us, and this is 0.4 here. So just to confirm that, so everybody sees what we're doing here. 1.1 and 0.4, where foxes are 0.1 and 0.4. So let's see which one is which. Delta must be the 0.1. And gamma must be the 0.4. Let's see, what is it? Growth and death rates respectively. Okay. So we should be able to get a graph like this. They go at 100 periods, right? And if you graph one stock against the other, we should get this cool looking graph. So let's see if we've replicated it faithfully. So we want X on here, we want Y on here, right? And we want another graph. We want X and Y again. So we're going to add, we'll do it the other way. X, we'll add Y, but we want scatter, and we want to connect the points. Okay, so scatter and connect the points. So let's see, and we're got to go out to 100. Right, okay. Let's use
How did you know to do a scatter plot? How did you know to do that?
That's just how you do it.
Okay.
Okay. And so just let's see if we've replicated. Looks like we've replicated that model, right? You see the scatter are the ordered pairs here, and then they'll connect the dots makes, they do it here for different values of the coyotes, I guess. Are they coyotes? Foxes or whatever.
Foxes.
So for 10, it was, and so we should be able to bring it in further if we, I didn't initialize outside here. I could have done that. We could have, if we say,
initial value of Y. Okay.
and it was 10.
Yeah.
Initial Y. So we'll run it again. And then it looks like it's telling us in Wikipedia that that the initial value of y sub 0, it can be 1, 2, 5, and it goes makes this thing smaller or bigger depending on what you do. So if we would turn the wheel here, now the scales are changing here, so it doesn't necessarily look like it's, but if we kept the scales the same, it would show that. Okay. So, all right. And of course you can, you could look at, if we wanted to loops that matter, we could start to ask questions, which loops are dominating and when. Now, at the end of the simulation, it's what is it telling us here? Undefined. Okay, so it's a little confused there. What if we back up a little bit here? So the major negative loop at this point in the simulation is accounting for 70% of the model's behavior. So you can see the shifting feedback loop dominance here. Depends on watch over here in the table. You see how the percentages are changing there as it proceeds over time. The dominance of the loops is changing. That doesn't happen in a linear system. Okay. All right, so let's pause for just a minute here and ask the question, do we see that? We took a famous model that has nothing to do with system dynamics, and we said, okay, the traditional math, I'm not entirely sure that that's intuitive, the traditional math. I've had engineering students at WPI, oh, that's intuitive to me. Like, bullshit, you know?
I don't think it's intuitive at all.
I'm not ruling out that there's some kid somewhere, some mathematician somewhere, some smart person somewhere, or 2 or 3 or 75 of them in the world, where that they look at those equations, they're like, oh yes, it's crystal clear. But most people, that's not the case. They will memorize it, they'll spit the solution back or whatever, but they won't really intuitively understand it. There were so many econ models that I didn't realize it at the time, but I had just memorized as a student. When I started studying system dynamics and translating them, I never really I realized I didn't really understand them. I was just memorizing them. And you start to intuitively understand the models. Okay. So that's okay, right? I mean, I want to make sure we're all saying or acknowledging that we got that under control, right?
Mm-hmm.
Okay, now I still think this isn't terribly insightful. Might be better than the Wikipedia presentation. Okay, I got bathtubs, I got faucets here, but I still think it's a little on the weak side, personally, in terms of like if somebody wants to really understand what's going on here. So can we make this better? So let's talk
about make it about foxes and rabbits.
Okay,
just changing the labels would help my brain.
Okay, so right. So one thing we can do is we'll call this, rabbits, and we'll call this fox and initial fox. Okay. Now, when you got a net flow, you got the ins and the outs all in one equation. And sometimes that's just the best way to do it. But other times you can do it that way, but it's not necessarily the best way to do it. Okay. So I think we have that situation here. So if we look at this equation, again, off to the right-hand side, we can see that, right? We got beta times rabbits times foxes. That's the outflow of rabbits. That's got to be rabbit deaths, right? And think about it, it makes sense. Right? Because the rabbits are being eaten, right? So if you look here, minus beta times rabbits times fox, what I'm going to do is I'm just going to copy the beta times rabbits times fox, and I'm going to paste it in here. Okay. And of course, we're going to need rabbits in there, right? And we're going to need fox in there. Okay. So let me try and move stuff around a little bit here. This might get a little messy here for a while, and we might have to fiddle with it, but I need fox in here. Okay, and we'll clean this up as we go along here. But so you need beta times rabbits times fox. I need beta. Where's my beta? Okay, so I don't need it over there. I need it over here. Oh, and it disappeared, right? The warning sign. So I don't need a minus sign because it's an outflow here, right? It knows it's an outflow. So there's no need for a minus sign. So over here, we move this away, and now I need alpha times rabbits. And that, of course, is going to be rabbit births. So alpha is going to be rabbit fertility coefficient, let's call that. Right? And think about this. We have beta times rabbits times fox. The rabbits and the foxes got to mathematically interact for the fox to eat the rabbits, right? And so beta is kind of the productivity of the foxes getting the rabbits, right? So we can call this maybe fox productivity in eating or hunting.
skills. Hunting
fox.
skills.
Fox
Hunting.
productivity
Yeah, there you go.
or skills, what it doesn't matter. Okay. All right. Now notice here I still got a biflow. Let's make that a uniflow. That'll clean that up because the births are going in, the deaths are going out. Now over here I can do one of these moves. Maybe that helps me. To be honest with you, I'm doing this in real time, so I'm not entirely sure that was the best idea, but it cleans up that a little bit over here. Okay, what do I have here? I got the minus, the outflow is gamma times the number of foxes. Fox, that has to be an outflow. That's the deaths. Right, so it's going to be the foxes times gamma. This would be fox deaths, and this would be
That's right.
fox times gamma. And over here, see, we have fox times gamma. And the minus sign, we don't need the minus sign because we now have an outflow. Right? And this would be, fox death fraction.
When you use fraction versus rate, I always get that confused. Or does it matter?
No, I don't think it matters. It depends on the terminology. Forster always called flows rates, but that confuses it with interest rate. So you have to kind of just define what your meaning is of your various variables. So then over here we have delta times rabbits times fox, but that's an inflow. So we got to make that one way in. And what we're saying here, or what Locke and Volterra are saying, is that when the foxes can eat rabbits, they reproduce. When they're starving, they don't reproduce, or their reproduction is cut back. And this is true, the female of the species, when they're starving, doesn't often reproduce, right? You would know that better than me, Suzanne, right? So you need foxes. Yeah, that's very common. So foxes times rabbits times delta. So this would be the, I don't know, effect of food, something like that. Okay. And so that would be that parameter, right? We just give it a more elaborate name. And then for the food to have an effect, the fox have to interact with the rabbits. If we look here at this equation, if there are no rabbits for the fox to eat, what does this flow?
0.
Rabbits is 0. What's the flow? What's rabbit deaths?
The death rate will stay the same. Or it will increase, I guess. The frequency. at
Rabbits
which they
are
die.
zero.
Yeah.
If you replace the
Rab-
rabbit, in there-
Rabbits are zero, the
Yeah.
death rate is zero.
yes, there won't, because there's nothing to eat, so that it'll
Right.
be. So what's that called?
A problem.
The limit.
Call this fox births.
Uh,
No,
Hunger
that's
Games.
called first order control,
That's right.
right? When the stock is empty, turn off the outflow. Okay, how about here? When you got outflows, good modeling practice, you see outflows. Do you need first order control? You might not, but if you do,
Yes.
so when the foxes are zero, the fox death flow is zero. So we have
Right.
happily, Lotka and Volterra have given us first order control. Yes?
Yes.
So now what do you see with the model? Now that we've made the names more, and you could name these whatever is more relevant to you, or you're Suzanne, you're a veterinarian, so there might be technical terms for these things. I don't know. I'm not a veterinarian, so I just do whatever, but you get the idea. So now what do you see in the Lotka Volterra model? And I will get 100%, I bet a year's salary, Lotka and Volterra did not know this, what we're doing right now. So what do you see in there? If you got an oscillation, which we do, let's run it. Let's make sure. Okay, so it's still okay. What do you see? If it's oscillating, we must have a major,
Feedback loop.
what kind?
It's going to be a
What causes oscillation?
balancing loops.
Yep, major negative loop, and we got one. But what else do you see hidden in their model? 4 minor feedback processes,
Mm-hmm.
right? Like I say, I'll guarantee you they didn't know that. And they're dead. So we know stuff that they didn't know. Look at this equation. Have you seen that equation before?
Yes.
What is that? Molecule number
1.
1. How about this one here?
It's number 2.
Molecule number 2. Now these ones are a little more tricky because they got the stocks multiplied in this, and we know it's got to be nonlinear because we got flow equations where stocks are multiplied together.
Right.
But you say, I kind of understand it. It's just a little bit a jazzed up version of molecule number 1 here and of molecule number 3. Sorry, molecule number 2. Half-life, doubling time, and all that.
Mm-hmm.
Okay. And then we got variable names that are more intuitive, and we reproduced exactly, what those guys were, or what Wikipedia is showing us that those guys were up to, right? Okay. So again, several reasons for showing this. One is the skill set of recognizing some traditional math, like, okay, I'm not afraid of it. I can understand what's going on. I can translate it if it's the right kind of math. If it's set theory, you can't use system analysis. It's partial differential equations. You can't, but if it's the right kind of dynamic math, you can translate it directly into its equivalent system dynamics representation, and then go beyond the direct translation to make it even more insightful, not just in terms of the names of the variables, but in terms of what kind of feedback processes do we have going on here, right? So, and you can do that. I don't teach it in this course, but I do that a lot. Most dynamic econ models are in difference equation format, and you can do the same thing with difference equations. It takes a little more treachery, but it can be done. And I'm telling you, I blow the socks off my fellow economists when I show them their own models or famous models that they didn't make, but they're familiar with, or in all the literature. And you show them it translated from the traditional math into this format, and how there's feedback processes and whatever. they're like, oh my God, I never knew all this. You know, they're like, what the heck's going on here? So how about this? You can just give it a, what's the causal loop diagram? There it is. You just want to look at the feedback processes. Right, the little button up here, go back and forth. Yeah, you got to have it in when it's run for some reason. I don't know why that is, but there it is. And if that's too big, usually they make it giant for some reason. I don't know why it's so giant, but you know, if you wanted to copy and paste it into a paper or something, or make a slide out of it, right?
So the question I have, Mike, is I don't know that I could take an equation like that. I mean, I know that some people look at equations like that and it just sings to them and it means something. Like they see a graph or whatever. I mean, I don't ever see that. I guess I could memorize those things and maybe figure out how to translate it into a system dynamics diagram. But what my brain does is I can see the stocks and the flows. And if my thinking is that I can learn the model structures and I can learn the math by seeing the model structures. Like I can see the model structures and it says something to me. I can look at an equation, it says nothing to me. What does that say about my brain or the application of system dynamics?
Well, I argued earlier this evening that most people see this and they, you know, like, I have no idea, it looks Chinese or something. Or they'll go, oh yeah, like a Voltaire, yeah, and they think they know it, but they've really, like I did, just memorized these models. They don't really intuitively understand them. And then you show them this, and they're like, oh, I didn't know all these are feedback. What do you mean feedback? You know, it's a whole new, like, taking a 1929, almost 100 years ago model, very famous. Every friggin' differential equations class on planet Earth does Lotka-Volterra, and show you it in a different light, right? It's not just changing the letters. Well, they used X and Y, let's use G and H or something. It's not that. It's
the relationships.
faithfully replicated, but now we're talking about it in terms of stocks and flows and feedback loops, right? And for that matter, limiting factors. When the rabbits are gone, that's a problem for the fox, and vice versa. So it's just a different way of looking at traditional math stuff. Now, if you're going to build an original system dynamics model of something, you know, you're not going to be necessarily doing this. You might do a literature review first and say, all right, the famous, you know, Smith and Jones, you know, 2005 did this famous model, and it's like this. And then you say, oh, I can take that and understand it better. So that's useful to be able to do. But you wouldn't be doing this if you're doing an original model from scratch of something. You're not doing this, right? But it's a good skill set to have in your hip pocket, right? And to then take a look at this and say, all right, what do I got going on here? And what, you know, you still have to run the simulations, but you say, I have some idea of what might be going on here. If I trace this through and there we got a negative loop going on here, a major negative loop, I have some intuition that tells me what might be happening here, even without running a simulation, right? So on and so forth. Okay.
I think that's, you know, part of the value of this course for me is there's a different strategy, at least in my brain. I don't know if this is true for everybody, of learning how to learn this type of material. You know, the way that I learn histology, which is microanatomy, is very, very different than the way that I learn art history. Okay. The skill set is completely different. And I think part of this is learning how to learn system dynamics is what's going on here. And I think the molecules and how they behave and the fact that they're building blocks makes so much more sense to me than originally how I was introduced in this course. And I don't know whether that's just the way my particular brain works. What I did notice when I took this course with Oleg was actually one of my study partners who I've never met before. He's like at that time, he was like the #2, the assistant chief of police for Worcester, Massachusetts. And he just gets to
Yeah,
take,
I know who that, yeah, I know who, yeah.
and I'm trying to remember what his name is. It will come to me in a minute.
Scott.
Super nice guy. But he really struggled with the whole concept of first, second, third order, and then they would get into these aging changes and how information or material can flow through these aging changes. Like he couldn't seem to grasp that. And to me, that idea of things accumulating and taking, having delays because it takes a while for it to leave a stock, he just really struggled with that and couldn't apply it to his world. And I think part of that is how you learn this. You have to learn how to learn this for your brain, which may not be the same as everybody else's. And I think that's part of the big challenge. And for me, I don't know that I could ever take equations like that and translate them into a system dynamics model, but I could probably go the other way eventually. Learning
Well,
molecules
yeah,
and
so some things, chaos. You might say, that was very interesting, but I can't see myself ever worrying about that. And the
I
answer
see the value in it. I don't know that I could do it.
Well, what I'm getting at is you might say that, oh, that was interesting, that was kind of neat, but I just don't see the need, I'm not going to do that. And that's fine. Not every aspect of everything is for everybody in every situation, right? It just kind of depends on what you're doing and so on and so forth. I'm multitasking here. I got to find something on my computer while we're talking here. So, some of the stuff is I offer to you as part of the story and some aspect of system dynamics and it may or may not be directly, your cup of tea for what you do, how you use system dynamics, right? I'm just looking for something here.
I'm just wondering out loud whether, because people learn differently, there's just different parts of this that will strike different people differently and flip their switch and they'll get it. If I'm ever going to be in a situation where I'm facilitating a group of people and we're drawing and building causal loops diagrams and then creating stock and flow diagrams for them. And if somebody came up to me and said, okay, well, show me all the math behind the stock and flow diagram and derive the equation that helped you build this, I would cry and say, here's my partner and let him explain it to you.
Right. So, yeah. So, no doubt that, again, not everybody can be an expert on everything, right? So
Right.
System dynamics, as we were sort of chit-chatting earlier, is very deep. There's a lot that goes on, just facilitation, as we discussed.
Mm-hmm.
Being able to work the room, so to speak. Not everybody can do that. So you might be the world's greatest modeler, super talented at modeling, at the technical aspects of modeling, but not be able to work the room, to facilitate, to extract from experts and stakeholders what they know. You don't have the presence, whatever. I don't know what. So you got to find out what you kind of have to be exposed to all the stuff, right, in the field, and then pick what you're good at and what's useful to you. And when it's something that's useful to you and you decide you're not good at it, you got to find somebody who is to help you.
Right. No, that makes sense. But
right.
I think it's just very interesting how different people learn different things, different subjects differently, and how I just know for me, making that transition from undergraduate, having a liberal arts degree, and then going to, biology and chemistry and stuff. I mean, I struggled for a while until I had to learn a different way of learning it. And I think system dynamics is the same thing. I just think with Ashley's background, and like I'd love to hear your perspective on this, Ashley, because with your background and what you do, you know, how do you perceive the way to learn this for you? I guess I'm interested in knowing that.
Yeah, so I mean, my I did my undergrad at the Air Force Academy, which is fairly
Math
fast-paced,
rigorous.
and it is actually more liberal arts than you would imagine, because they require you to take a lot of English classes. But I got a systems engineering degree. I thought I was good at math before I went there, and I realized I was mediocre at math probably, but I made it. And so now I'm in intelligence, but I'm still really interested in integrating systems thinking, or like the rigor of systems thinking, into kind of that softer analysis, because you really do need that to be good at it, and to see things other people won't see. So I guess that's my background, but I mean, I did learn the math. It was 7 years ago and I haven't used it since. So I'm also just trying to relearn it. But a lot of what I mean, I take notes all class because I kind of have to like think through and write it down and sort of like work with it on the paper to get it to click in my head a lot of the time. So that's sort of my learning process. I also really like reading. I learn very well by reading, which is why I'm trying to read the books too. But yeah, so I mean, I don't find the math the easiest part, but it's slowly coming back in the dregs of my memory.
So now let me tell you a story. You should be saying at this point, this freaking guy Mike has a lot of stories.
That's a story for everything.
Oh my God. So it's back in 1988 or 1989. And I'm sitting in I'm living in South Bend, Indiana, and I'm reading the Chicago Tribune. Now, what's quite common is like in Worcester, Mass here, and I'm guessing in Arkansas, it's probably the same. You know, you kind of read the Worcester paper and then like the Boston Globe, right? Sort of the big nearby big city paper, and then the local paper. So in at Notre Dame, you read the South Bend Tribune, and then the Chicago Sun-Times or the Chicago Tribune, or some people like the Detroit papers, whatever. So, you know, you kind of had a big city paper and a local paper. So I'm reading the Chicago Tribune on a Sunday morning, drinking my coffee, just paging through it, what looks interesting and whatever. And I come across the following. So we're going to share our screen again here. And so can you see all Clarence Peterson's?
Yeah.
All right. So literally, this is quite literally a Xerox copy of what I came across. So a Harvard University mathematician has devised a teaching plan that, as he puts it, relates mathematics to a topic that's already on the minds of many college students, the time evolution of a love affair between two people. So Harvard's Stephen Strogatz, he's at Cornell now, described the plan in Mathematics Magazine. I subscribe to Mathematics Magazine. Do you? No, I don't really subscribe to it though. Under the sexy title, Love Affairs and Differential Equations. He bases his ill-fated love affair on the story of Romeo and Juliet, except it's not their families that keep them apart. It's Romeo's fickleness. The more Juliet loves him, the more Romeo begins to dislike her. But when Juliet loses interest, his feelings for her warm up. She, on the other hand, tends to echo him. Her love grows when he loves her and turns to hate when he hates her. According to Strogatz, a simple model for their ill-fated romance is the following, where R is Romeo's, J is Juliet's. It's important to know that the positive values R and J signify love, negative values signify hate. It is also helps to know that the parameters A and B are positive to be consistent with the story. That's a little misleading, but hang on here. Or so says Strogatz, who goes on to note that the sad outcome of their affair, of course, is a never-ending cycle of love and hate. Their governing equations are those of a simple harmonic oscillator. Well, the news is not all bad. According to the equation, instead of equations, the harmonically oscillating Romeo and Juliet managed to achieve simultaneous love 1/4 of the time, quote unquote. So so Clarence Peterson is basically saying somehow he got the hold of this article. in Mathematics Magazine by some dude named Stephen Strogatz, and he's claiming that these two weird equations are Romeo and Juliet. So he's kind of quoting the Strogatz's article and being a little sarcastic. And then he says, so Clarence Peterson telephones his father, 29 years retired from the math game, to see if he had any suggestions for making the Strogatz formulations even clearer. Said he, I am mostly into gardening now, son, but my guess is that lacking a Harvard education, you're probably intimidated by the reference to the Shakespearean tragedy. Substitute the Hatfields and the McCoys and see if that doesn't help. Now, this thing was just filler on the back of the Chicago Tribune, the back of the first section. So I'm reading this and I'm going, well, hell, I wonder if I could just, I've just pulled up Stella at the time. And I said, well, hell, I'll just model this and I'll probably, send it to Clarence Peterson for giggles. Like, here's how you understand this. What I noticed is that it was a little more difficult than I had thought. I thought it would be a 4-second thing to do. But I realized that, wow, to program up this model and to sort of address all of the points in Clarence Peterson's thing required a bunch of system dynamics modeling skills, right? So I told this to John Moorcroft, and he says to me, well, you should write that up in a paper for the review because it would be a great exercise for teaching system dynamics. So I did that. So here's the article. I don't know what year I did this. What the hell year was this? It came out in 93. Okay. So it was around the late 80s when I started goofing around with it. I mean, I didn't immediately call it Moorcroft. I just saw him the next year at the conference or something, and we were talking about all this stuff. And so I started playing around. And then I noticed in the original article, he talks about Stephen Strogatz's, piece in Mathematics Magazine. So I went and I got that original piece. So here's Mathematics Magazine. Okay, and there's the model, right? But then looky here. Strogatz says I got a more complicated version of the model with some other interesting romantic styles in here. Okay. So I said there's even more to this whole thing. So the question I would give to the students, and this is in the course, if you have access to Canvas, the exercise is like quiz number 8, is basically to build this model here and see if you can answer some of these questions. How do you know if Romeo and Juliet managed to achieve simultaneous love 1/4 of the time? How can you do that? Is it really a good model of the Hatfields and the McCoys? Okay. How do you know it's a simple harmonic oscillator? Okay. And then go to Strogatz's model, his more complicated model, and see if you can name the romantic styles and whatever. So it's really quite an interesting exercise. There's a lot going on here. It doesn't look like much, but there's really quite a lot going on here in terms of system dynamics modeling skills. And so I published that paper, and it turns out there's this dude in Italy who wrote a whole book. This is just a paper, but he wrote a whole book on love affairs and differential equations. So he cites my paper and Strogatz's paper at the beginning, and then he goes on and he has a whole crazy. So you can see there's a lot going on here. Then he turned it into a book. It's not just this whatever he's doing here, but it's sort of generated a cottage industry of system dynamics modeling. So let me just show you a few things here. I don't want to dwell on this. I'll leave the exercise if you're interested, and we want to move forward anyway. But if I were to quickly model this, okay, this Strogatz thing, okay. So he says there's R for Romeo's affections, and I'll pull it back up on the screen here in a minute. there's J for Juliet's. And just to refresh your memory here, so dr dt and dj dt, so we have A and B are parameters, and J and R are the stocks. So we got the R, dt, and dj dt. We have little a and little b. Now, it's not as obvious in this case like it was in Locke Volterra, but we really need biflows here, because one clue is they talk about negative values are hate and positive values are love, I guess. All right. So, you know, you got to go with some of the clues. There is a minus A here. This says that the thing says that they're both where it's misleading. It says, let's see, the parameters A and B are positive to be consistent with the story. Well, but you look down here, it's a minus A. So it's not really, it's A, and then you stick a, which is positive, and then put a minus sign in front of it. But it has to go in the opposite direction, so that you got to have a net flow rather than a uniflow. So, you know, this is going to be, you know, whatever, a minus, you know, 0.1 or something. We'll call this 0.1. I don't know. I'm just making this stuff up. And we need like this. So it's a B times R. And over here, it's A times J. Did I make a minus number in here? Yeah, I did. Negative number. And, you know, you can make this just, I don't know, 1. 1. Okay, so what do you see so far? That should be this right here. Right? So what do you see? System dynamics, intuition.
There should be there's missing feedback from our stocks. We need to have some.
We're just replicating Strogatz.
Okay.
So I think we faithfully replicated. We got a major feedback loop, right? And with the minus sign in there, it's got to be negative.
Right.
Now, I don't remember what parameter. We can look at the paper. So the parameters, these little models usually are sensitive to their parameters. So, because they're not feedback rich. And I'm not sure if we want 20, something like this.
When you drag like that, do you click on the stock and then let go when you have it?
Once you're inside the graph,
Okay.
yeah. So
Okay.
let's see what happens now. Okay, that we probably got to go farther. I don't know. Okay, so there's your simple harmonic oscillator. Now, what I first did was, what if we made this my default? Okay, so it's a little hard to see there, but this is a good system dynamics modeling skill. What kind of oscillation does it look like we have?
What are our descriptive options?
Sustained, damped, exploding.
Sustained. Well, it's mildly exploding. Mildly exploding.
Okay, it's
over a very long
exploding.
period of time, yeah.
It's exploding. So the question to ask when you see that, good modeling practice is it exploding because of integration error, or is it exploding because of the stock flow feedback loop structure? So another way to take a look at this, we can use that scatter and connect the points and say we're going to have Juliet and Romeo. And I know what the problem is here. There we are. So what do you think about that? Looks like
It's
it's
definitely
exploding,
exploding.
right?
Yeah.
So the question is that due to integration error, or is that due to the stock flow feedback loop structure? How would you find out? You should do this with all system dynamics models, not just with Romeo and Juliet. This is what I mean. It's chock full of modeling best practices. How would you find out? Why is it exploding? Is it due to integration error or to the stock flow feedback loop structure?
You would change your integration method and see how the model behaves.
And or make this
Or your time step. Yeah.
Yeah, so let's, we can make it a second order.
Oh, that's much better. Well, that's
So it was due to integration error, right? We used the Runge-Kutta method to clean up same DT. So we're not going to do the whole thing, but if you go through the second Strogatz model, you'll find that under certain circumstances, you'd have an exploding oscillation, but it's due to the stock flow feedback loop structure, not due to integration error.
mm-hmm.
Okay. How about, can you use 1/4 of the time they're simultaneously in love? Can you see that here easily?
That's why I kept trying to figure that out.
A little hard to figure out here. How about down here?
Well, it's at 1/4 of the time they're both in equilibrium.
I don't know if I'd say equilibrium. 1/4 of the time they're in the northeast quadrant.
Okay.
They're both positive. 1/4
Right.
of the circle, right?
Right.
That's much easier to see than trying to figure that out from up here, right?
So,
Yeah.
as someone who just got married, is there a model that shows you being in love simultaneously more than 1/4 of the time?
Good. That's a good.
What
question.
would that circle look like?
Yeah, right. Well, this Italian guy has all sorts of crazy stuff, so you got to really look beyond these various. So, but let me show. So, if you go to his Strogatz's original paper, if you look down here, see if I can make this bigger. Okay, what do you see here? That's his more complicated model. You see two flows.
Yeah.
Flowing to a stock called R and a stock called J.
Mm-hmm.
And the flows involve, the flow into R involves J, Juliet's affections, but it also involves R. So R involves R and R involves J. Right? And same for Juliet.
There's an interdependence.
Well, but also there's minor and loops and major loops,
Right.
Major loop and minor loops.
Mm-hmm.
And he's talking about romantic styles here. Well, those depend on the minor loops. What kind of romantic styles it is. So that kind of sort of answers Ashley's question about 1/4 of the time or whatever. You get what does he call it here? An eager beaver style. And what's the other one? So he tries to get his students, Strogatz, to name the romantic style. So that's in the paper as well. So if you look at my paper, because I show all the answers here, this is just a Xerox copy from the olden days. But, you can see the stuff we're discussing here, 1/4 of the time, and now here's the more complicated model, and you should be saying, oh, that kind of looks like Lacca-Volterra, right? So we got major and minor loops. We even did that in the PowerPoint slides where we had, just the generic. So what happens when you got a major negative and two minor positive loops? Oh, now you've got exploding oscillation, but now it's not due to integration error. It's due to the minor positive loops kicking it. Every time it goes around, it kicks it, adds some energy. Or damped. Remember the PowerPoint slides?
Mm-hmm.
Right.
Mm-hmm.
So anyway, all the answers are there if you want to, but so it's kind of a neat exercise because it forces new folks. It looks so terribly simple, right? But it really isn't. There's really quite a lot going on here. So for whatever that's worth, it's kind of an interesting thing.
So now, Ashley, you have to go and you have to make like the newlyweds version of this to solve it.
Well,
This
this
is what happens when you're newlyweds. This is 10 years down the road.
honestly, this Italian guy, and there's other people doing stuff with this. It's actually this thing has been used at Cornell, my paper at the West Point. Speaking of the military academies, I know they used it at IC Systems as one of their podcast things, and it was recently used at one of the podcasts from the System Dynamics Society. So people like it. It's terribly simple. It's not that big a deal, but it resonates with people. It's like they can kind of relate to it or whatever. And like it's a really horrible model of the Hatfields and McCoys, like Clarence Peterson, dude, or your dad. You know, that's no good for the Hatfields and McCoys, right? But it's worth playing around with just to kind of get the feel of some of these. Get in the habit of saying, all right, I see an exploding oscillation. Why is that? My habit is I'm going to cut DT, make it smaller, or use a different integration method and resimulate. It's better to resimulate longer too, just to see what happens as you go out farther past the reference mode, just to make sure that something weird doesn't happen. Something goes, or some crazy thing like that, right?
Is that what the girlfriend? Is that when like the girlfriend or the boyfriend comes in the picture, or later on in the marriage?
As you might imagine, you can go like this Italian guy. You can go all over the place with this stuff. The guy wrote a whole book on it. That was just a paper that he wrote, but then later on he had a whole book on the friggin' thing. So yeah, I mean, you can, and you can get into psychology and studying interpersonal, whatever, on and on. So leadership, subordinate, all these individual level interactions of like two people or something. So anyways, all right, so there you go. So where are we headed now? I know we're a little past 8, but we kind of chit-chatted at the beginning there, but where we're headed now is to say, all right, we're beginning to see nonlinear models now. All right, we're beginning to see stocks multiplied by stocks or ratios of stocks. We're beginning to see deviations from the linear pattern in the flow equations, okay, which means you really do have to simulate to find a solution, except there is some treachery in special cases and mathematical treachery in special cases where you can analytically solve a nonlinear model, but it's few and far between. Generally speaking, for 99% of the models, nonlinear models, you got to simulate to find the solution, and you start getting into shifting feedback loop dominance in the linear space and abrupt changes and whatever. Then that's where all the interesting stuff happens, right? All the counterintuitive stuff and what have you. So we really got to go nonlinear. So we've dipped our toe a little teeny bit in the water with this nonlinear stuff, but we've been looking at the traditional mathematics of it. And we're going to start to see that there's different ways in system dynamics to make nonlinearities that are more the signature way of doing it. There's another thing I don't know if I'll do this next week or not, because I think it's like read the room, Mike. I don't think that translating ODEs into their equivalent system dynamics representation is necessarily exciting for folks.
What's an ODE?
Ordinary differential equations, right?
Oh. I would like to see that.
I mean, it's. I'm not saying it's horrible, but for folks, but I don't get the sense that people are saying, "Wait till I tell everybody I can talk to about how."
I might not tell everybody I talk to, but it might help me understand a little bit better why I was tortured with differential equations in calculus, that I couldn't understand why this was of any value to anybody on the planet.
So, let me tell you what I'm getting at here. So, all right, so here's the exercise, the homework or the quiz exercise, whatever, where you do the Romeo and Juliet thing. If we were to, so there's a chunk of the course that we could do where we talk about, well, the mathematicians aren't usually so nice as to break out the individual flow equations. They roll them up into a more complicated thing. And how do you unroll them first so you can translate them? But the other thing is, if we would say, we would say Richardson's arms race model. I don't know what comes up here first of all. Oh, they're going to make me download it. So I'm just trying to find something real quick here. Richardson's arms race model, introduction. Okay. So Richardson was, this is not George Richardson. Richardson was Lewis Fry Richardson was a physicist, but he was also a Quaker. And he was very much alarmed prior to World War I at the arms race going on between Britain and Germany in terms of building battleships. So he came up with this very famous model here, which is not surprisingly known as the Richardson's arms race model. Okay. And, I usually go through this one as well, but I think we're getting the point. But again, what do you see here? Again, this is a super, super famous model. I mean, we did our own arms race model, but this is the famous Richardson. So what do you see there?
Differential equation with
the second order system.
Second order system, and it has more parameters.
Okay. So dx dt is a flow. Where is it flowing?
To X and Y.
No, it's flowing one place. The change in the stock X over time is the flow, and it's flowing to X. And the change in the stock Y over time is flowing to Y. And what are X and Y's? Y, the level of arms of the two nations.
Okay.
Number of battleships or missiles or whatever the heck it is. Okay. And then they tell you here somewhere, equilibrium, So, well, I just Google this real quick. But so what do you see over here? So the change in the building of battleships over time is a function of what the other guys have, which is Y, the stock of, Germany's battle. If this is Britain, Germany's, and the K is the parameter. If it's 1, they'll try and match them one battleship for one battleship. If it's 0.5, they'll build a half a battleship for every battleship the Germans have. Minus alpha times X. It's molecule number 2, right? It's the stuff is rusting away, becoming obsolete. So this is a net flow equation. We got stuff going in, stuff going out in the same equation. So stuff going in is K times Y. So what do the other guys have? Times a weight, parameter K. I'm losing some of my battleships to obsolescence and rust and whatever. And then G and H are like grievance terms. That was kind of like in my model where I said, if we want to be safe rather than sorry, I'll pad my estimate. So the inflow would be G plus K times Y, and the outflow is alpha times X from X. And then the same thing for the other side.
I see.
Right?
I might get this if I were to keep doing it. I get that.
So we got, it looks to me like we've got a minor loop on each side and then a major loop. Is it linear or nonlinear?
It's nonlinear.
So we got a pattern. The pattern is alpha 1 times S1 plus alpha 2 times S2 plus alpha 3 times S3. And then the U's are, so alpha 1 times S2 minus alpha 2 times S1 plus U1. It's linear, right? It follows a linear pattern
I
on the
don't,
PowerPoint slides. So it's tricky. If you compare it to Lotka-Volterra or, well, how about Strogatz? Were those models linear or nonlinear?
I don't know.
Linear, right? You weren't modeling Romeo and Juliet's emotions were not being multiplied together or ratio them or anything like that, right? In Lotka-Volterra, the predator and prey had to interact mathematically. So the Y and X were multiplied together. You broke the linear pattern. See, they all look kind of the same, right? But you got to be a little careful. It's a little tricky, but can you see the feedback loops are kind of there, right? You have to kind of lay it out, but you see?
I think I would have to try and build it to be able to
Yeah.
really see it.
No,
When the feedback loop, when the flows are biflows, it's hard for me to recognize that in this sort of a format. I would have to go through the process of trying to create the model, and then I would probably recognize them as biflows. But it is hard. It is
Yeah, so
kind of the math.
let me see if I
Okay.
can find it right quick here. I know I have this model somewhere. Let's see if I won't belabor it if I can't find it. I just was doing this kind of on the fly. So you can see what it looks like. Oh, wait. Okay, so and this is actually a good way to lead us into the next. So you see, we got to dismantle those molecule number 2 in here, but there isn't minor loops on the build side.
Mm-hmm.
Right, you had those grievance terms, and then you had, so remember it was your add your grievance term G, and then it was your parameter K times what Y, the number of battleships that Germany had, and vice versa. Right, now there was a paper I found where it's kind of interesting. The paper said, really, you can add limiting factors to the Richardson's arms race model, like government budgets and stuff. And now what do we have? We have kind of the limits to growth kind of scenario, right?
Mm-hmm.
So we're heading towards, so this turns the linear Richardson's arms race model into a nonlinear model. We added a nonlinearity because floors and ceilings need to need to have nonlinearities that describe what the system does as it approaches the floors and the ceilings. Okay. All right. So where are we headed? Okay. So we can, if we want next time, to take a look at when these ordinary differential equations are more nasty. How do you decipher them and turn them into nasty? I don't think that's necessary. I don't think anybody needs to really know how to do that. If you want to know, I'll send you the slides are probably even on the Canvas site. But where we're headed now is we're going to really start going nonlinear. And that was a peak. Now we're going to have S shape or S overshoot and collapse, limits to growth kinds of stuff. And we're going to start to say, all right, I get it. If there's this pattern in the flow equations that makes them linear, right? And if you deviate from that pattern, well, then the model's nonlinear. And that means, well, one of the things it means is you're going to have to simulate to solve it. Number 2, it's going to mean that there's the possibility of shifting feedback loop dominance and other counterintuitive behaviors that are, quite prevalent in the world. And that's where system dynamics is quite useful to reveal that kind of stuff, right? And then you can begin to think about limiting factors, because a lot of these simple models, they can grow forever, whereas in the real world, we're limited, right? We have cognitive limitations, we have budget limitations, we have physical limitations, right? So they're in the real world, they exist and they're important, right? So we probably need to consider incorporating them into our models. And if so, how do you do that? And we can say, well, you multiply two stocks together. Well, yes, that's the traditional pencil and paper 1926 way of doing it. But we have other techniques in system dynamics, including, most importantly, something called table functions.
Oh, yeah.
Okay, so we're going to start learning what table functions are and how they're used, they can be used all different ways, right? But we'll start revealing how that works. And then you can really start to build interesting and counterintuitive system dynamics models. And that when you're really doing a research model and, trying to reveal to intelligence analysts where their thinking might be flawed or where leverage points are in the system or whatever, you really need the table function tool and the capability of adding nonlinear relationships. And then where do I put in nonlinear relationships, right? So all of that really begins to open up really the value of this sort of modeling. Because I think, if you build a model and it grows, and then you say, if I make this parameter bigger, it'll grow faster. Let's see. And you hit the go button. Yeah, it grows faster. If I make it smaller, it grows slower. Okay, correct. Cool that you were able to formally represent that. But did you really learn anything from the model, right? Because, it's kind of like you didn't need to run the model to know that. It confirmed what you kind of knew, but but when you start adding these nonlinearities and such, that's when you start to say, I'm not entirely sure what the hell's going to happen here until I press the go button. And sometimes you're right. Your mental model's getting better as you play with the model, as you learn from it. But sometimes you're still caught blindsided. You're like, yeah, I didn't expect that. I thought it was some entirely different, right? And that's where you enrich your mental model and you start better conversations with intelligence analysts or military leaders or veterinarian associations or whatever, right? Where they're like, well, did you consider the following? Oh, wait a minute. What? And you put a few nuggets on the table that maybe they haven't heard before. Or it's something that's happening later rather than sooner. That, yeah, no, the short run, sure, but the longer run, we're likely to run into this. Oh, I wasn't thinking of the longer run. I mean, we're not in the United States, we're not taught to think about longer term stuff usually because we have to make quarterly earnings reports for our share prices, and there's political cycles, or you stand for Congress every 2 years, blah, 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 all that sort of stuff. So it's more of a pressure to deal with the short run, right?
I mean, I think that's one of the things that I'm really attracted to is the fact that it helps you weigh the consequences of your short-term versus long-term outcomes. And frequently there's costs and benefits to each one of those positions.
Well, remember when we did the counterintuitive, the characteristics of complex systems earlier in the course, we talked about better before worse or worse before better. It's very common with these kinds of systems. So yeah, you can shove the system hard this way and it does what you want, but then it in the longer run comes back and even is worse than it was before often. Or you shove it the other way and it's worse at the beginning and people are grumbling, but over time then it gets better. You got to cut the tail off the puppy quick or pull the Band-Aid off or whatever the saying is, right? To the suffer in the short run to
delayed gratification.
Yeah, well, and in Forrester's the urban dynamics thing, you had to knock down some dilapidated housing to make the city healthier in the long run and so forth. Right? So that you don't get all that kind of stuff typically with linear models. You really need the nonlinear stuff. And the signature way of doing that is table functions. So we're going to start learning how to do those and look at some interesting models that feature table functions. There was a table function in Homer's model. We played with it a little bit. just goofing around today. We really didn't delve into it because we hadn't discussed table functions
Right.
yet. But, we just had a bunch of hand waving about it's involving the psychology or whatever, but we'll show. And I'll even, we might be able to show the, leader subordinate thing that you were
Yeah,
interested in.
I really want to.
That's loaded with important table functions that
Yeah.
really cause the counterintuitive behavior. So we can take some time to look at that, and we'll look at trying to manage the deer herd on the Kaibab Plateau, which is sort of a mini limits to growth kind of thing. Well, and so okay, so that's where we're headed next. So this is class what? Was this 11?
11.
Okay. And we're in what month of the year? November or December? Yeah. So okay, we're getting there. A lot of other cool stuff to look at, but we're getting there. So the question is, am I whetting the appetite for more? See, that's
Yes,
the
I
question.
want more.
Is like, or
Absolutely.
is it like, for the love of God, enough with the stories, enough with the.
No, I find
the
the stories really valuable,
And-
and I'm really glad that we're recording this because I do want to be able to spend more time on the recordings and be able to get in my Stella and build this. And there's just a lot of articles and stuff I want to read right now. Is just a hard time.
Yeah.
But
Yeah.
I'm really-
Participatory sport. Gotta get in the game. Gotta get in the
yeah,
pool.
yeah, this is all good.
All
Okay,
right,
Mike.
so let's leave it there. Thank you. Hope you found some value in all my yammering here, and
Yeah.
we'll reconvene next week.
Okay, thanks, Mike. See you, Ashley.
Yeah. Bye.